Okay, 6.5 notes. The learning objective for today is to identify and perform dilations in the coordinate plane. So a dilation is essentially a similarity transformation. Now, a similarity transformation is a transformation that produces a similar figure to the original. We've already discussed congruence transformations, or transformations that resulted in congruent figures. That would include translations, reflections, and rotations. A dilation will result in a similar figure. A dilation is essentially a transformation that stretches or shrinks a figure by a scale factor. The center of dilation is the fixed point about which a figure is dilated. In this lesson, we'll generally be discussing centers of dilation at the origin. So we'll be dilating with respect to the origin for almost every problem we do. And the scale factor of the dilation is the ratio of a side length of the image to the corresponding side length of the original figure. So it's the scale factor by which we dilate. Coordinate notation for a dilation is important. You'll need to be able to do this. We can describe a dilation with respect to the origin, which again almost all of our dilations will be, with the notation x, y to kx, ky, where k is the scale factor. So when we say ky or kx, we mean k times x, k times y. So we just multiply each x and y coordinate of our points by the scale factor to get new points for each one. If k is between 0 and 1, that is, if k is a fraction, the dilation is a reduction. If k is greater than 1, the dilation is an enlargement, and you'll want to be careful here. If k is a fraction that is greater than 1, so an improper fraction like 5 over 4 or 6 over 5, those are still enlargements. So as long as it reduces to a mixed number that's bigger than 1, it's an enlargement. The example that we see here, we have a quadrilateral ABCD with these vertices, so we plot that here, and those are the solid lines. And then we use a scale factor of 2 to dilate, so xy becomes kx, ky. So for each point, we multiply each coordinate by 2 to get our new points. So 2 times 1 is 2, and 2 times 2 is 4. 2 times 4 is 8, 2 times 1 is 2, and so on, so we get these new points here. So when we plot those points, we see we have this dashed figure. Now when you do a dilation, you don't have to put your image in dashed lines. I just did that to distinguish for the notes. But our enlargement here, because it is an enlargement here, because our scale factor of 2 is greater than 1, we can see that our figure becomes bigger. Here we're going to verify that a figure is similar to its dilation. So we sketch the two figures that we're given. We are given ABCD. We do a dilation to form DEF. So we have the points ABCD right here dilated to form DEF. So we have ABC here, and we have our dilation. You'll notice that since k is a fraction that's less than 1, this figure that we get for our image is smaller than our original, so that's a reduction. Now, DFE and ACB are both right angles. We can see that with the points that we plot here. These are horizontal lines, those are vertical lines, and those intersect to form perpendicular angles. Now, because they're right angles, they're congruent. Then we just count to find the measures of those sides. So this one is 2, this one is 1, 2, 3, this one's 1, 2, 3, 4, and that one's 1, 2, 3, 4, 5, 6. We verify that they are similar by stating yes, they have congruent angles, and then we can use side and side, which gives us side, angle, side similarity. So we find that scale factor here, 2 over 4 reduces to 1/2, 3 over 6 reduces to 1/2, and again that's the scale factor that we use to create the dilation. So yes, they are similar by side angle, side similarity. On example 3, we are finding a scale factor. Scale factor is always image to original, so that's 1.1 to 4. We multiply that by 10 to get whole numbers in our fraction. We always want whole numbers in each, the numerator and the denominator. So we get 11 to 40, and then inches was our units here. So that involves just setting up really the scale factor as image to original. Now when we read diagrams, Generally, for a center of dilation at the origin, the point of the figure and its image lie on the same ray from the origin. But if the point of the figure is the origin, the image is also the origin. So imagine if you multiply here, point A is at 0, 0, anything multiplied by 0 still results in 0. So no matter what your scale factor is, that point will still be at 0. And we can see this occurring up here on this example, that each one of these points is on the same ray from your center of dilation. These dotted lines here represent the rays of dilation. We can see that down here too. Remember, any coordinate that is a 0 will remain a 0, so it'll just stretch out along that line. This one stretches out along this line, and this one stays where it is because it is the origin. And that concludes 6.5 notes.